So
Okay.
when we got to that step in substitution where we arrived at, mass A plus mass B in parentheses times acceleration, is
Right.
that set to 0?
No. If we go back,
I'm sorry, I just was trying to figure out what would be the solving. Right.
so when we added the two equations together, on the left-hand side, those cancel out on the left with the MVG. On the right-hand side, I have MAA and MBA added together.
Yeah.
And then I factored A out.
Okay.
Is that clear?
Yes, yes. Thank you. And then that's where we would solve from there by entering everything.
Yeah.
Okay.
Now, some people like sticking in numbers early on. There's nothing inherently wrong with that. It's generally recommended to keep it in terms of letters until the very end and then plug the numbers in. And there are times when it's very convenient to wait and times when it might make more sense to plug numbers in early. If friction is involved, I recommend waiting to plug numbers in. All right, force diagram. So let's break it up. I got my box 1, my box 2, ideal rope and pulley. Okay. Anything we can get rid of?
There. Are the boxes moving? Because,
Let's do friction last, speaking of which.
okay.
All right, so it's friction, save till the end, there's a reason for that. Trust me. How about weight? Which way is weight acting on what?
Isn't the box to the ground? So like,
Box to the ground.
oh, my bad. I don't know what you were asking. So like, you mean like the arrows itself?
Yeah, which way is weight acting on what object in which direction?
Downward, one.
Downwards on one?
And upward from the incline.
All right, all of this is ground, so just anywhere down here.
Okay. Would it be the same for number 2 as well?
Except,
Subscript will
Okay,
change.
subscript.
yes. All right. And it's an ideal rope, so we don't have to worry about the weight of the rope.
And then normal force, it would be, for normal force, it would be going up from, so for number 1, it'll be going up to the top left and then going down from the inclined plane itself because it has to be perpendicular. And then for number 2, it would be the same but with a subscript number 2.
And upright on the box good. All right, normal force is done. Oh, wait, no, it is not. One more pair.
The,
So going with Patika's gesture, so I got Y sub R, T, whatever letter strikes your fancy. All right, normal force done. Tension.
so from box 1 to the string, it'll be the arrow from box 1 will be going to the right, I mean top right, and then from the string it'll be from the same direction, the opposite direction like that, yeah.
And over here, similar.
Yeah.
And again, if you're gonna put subscripts in, those would have the same subscript.
Mm-hmm.
These two would have the same subscript as each other,
Yeah.
different from what I have over there. All right, friction. Which way is friction acting on box 1?
That way. So, wait, so It'll be
Well,
going-
first off, it's gotta be parallel to the surfaces of contact,
Yeah.
so it won't be that way.
Yeah, it'll be like somewhere.
Alright, so Robin was going this way and Abigail's going that way?
Yeah, so with the boxes, the pulleys would be moving the boxes down, or,
Alright, and this is why I saved it to the last. Box one or box two, it's either gonna go like this or it's gonna go like that. We really don't know, given the information that we don't know from the information that I've given you. So the direction of friction is either gonna be this way or that way, depending upon which way it's gonna slide. Now, in 110, I would have to say which way that they're gonna slide. In 151, I don't have to. I have to give you more information than what I've given you, but it is something that is solvable. Ultimately, I'm gonna have the weight of 1 times the cosine of theta 1 acting down the ramp that way, times the sine of theta 1 acting down the ramp that way. And over here, I'm gonna have the weight of 2 times the sine of theta 2 acting down that way. Which one's bigger? So, pull out the calculator, you type it in, you come out with the value, you figure out which one's bigger. For the sake of what we're doing right now, assume that it's gonna go this way. So if it's gonna go down that way, which way is the friction gonna act on box 1?
Yeah.
Right. Okay.
So friction 1, and then friction 1, and then friction 2, friction 2. In a proper problem, I would set it up with the starting at rest. I give you the coefficients of friction, and just set you as what's the acceleration. You would make an assumption, you get an answer, you look at the answer and go, all right, that works with my assumption. Or you look at the answer and go, that's completely opposite of my assumption. So I guess my assumption was wrong, let me start the problem over again. Luckily for you, I hated the problems that I had to do 3 times. Because you make an assumption, oops, that's wrong, let me start over again, let me do it again, oops, that's wrong, let me do it a 3rd time. I will go through a problem like that, however, I tend not to on tests just because I despise them as a student. But as before, I can put one on the test, test 1B, if you want. I would do it for you. Any questions before we do a test level problem?
That must be supposed to test level.
No.
Okay.
No, well, this would be a test level problem if I gave you the masses and the angles and asked you to find the acceleration. The next one is a test level force diagram problem.
What would a coordinate system for this one look like?
I would have probably I1 hat that way, J1 hat that way. And for here, I2 hat going that way, J2 hat going this way. They are not necessarily the same coordinate system because I didn't give you any of the angles for you to know exactly. Odds are this and this are not parallel, even though it might look like that the way I've drawn it.
We have a last in it, right?
Yes.
All right.
Let's set up the test level problem. I guess it's a wall. Alright. Didn't think you'd hear the screams. Alright. Now, a problem like this, I would break up the parts for you so you're not guessing about, if there's no pulley in this one, but if there were a pulley, is the pulley separate or is it part of the ground? I would break it up for you. So in this particular one, I'm gonna have the ground, man, rope, sled, boy. This is the problem that I refer to as man pulling sled with sun on. If you don't want to, I made it male-centric because, well, my experience. If you wish, mother pulling daughter, mother pulling son, take whatever combination you want, androgynous stick figure pulling androgynous stick figure. All right, so we've got so I'm going to have now, if I thought about it a little bit more, I would have made the original drawing smaller and the force diagram larger, but all of you are young and you have incredible eyesight. Is that a shaking your head to the eyesight or the?
Eyesight.
Half the people in here are wearing glasses.
What if you just delete the red?
Was that?
What if you just delete the red, so we can see everything?
Yeah.
All right. All of you have got this, I assume, drawn better.
Yes, sure.
Okay.
We're starting.
Let's do friction last.
Okay, so other is not there. There's no other.
Oh, I'll give you one other piece of information. I will tell you that they're accelerating to the right. Okay, good.
No, there's no other, right?
There's no other. I'm trying to think of it, for the test level force diagram problem, I'm trying to think if I've ever had an other in there. Maybe once, maybe not at all. Yes, Abigail.
Is weight going to the right because the man's pulling weight
Which way does weight go?
down?
Down. Or on the ground? Up, yeah. So weight is gonna be going down. So let's put that in there. Green, all right. So the weight of, well, everything, except for the rope. So I have weight of dad. Weight of dad. Weight of son, to B for boy. Weight of boy. Weight of sled. Weight of sled. And if you did weight of rope, I wouldn't take off for it, but ideal rope. All right, weight is done.
There's normal force between the kid, the sled, and the ground. So,
So two objects at a time.
so for the kid and the sled, for normal force between the kid, it'll be going up, and then the sled will be going down.
All right, so I got Y sub B, Y sub B.
And then there is a normal force again that's going up for sled and then down for ground.
And I think I mentioned this before, typically when I do the subscripts, and this is a me thing, I start from the top and work my way down, so this is my B, S, and I don't really use G here. But some people start from the ground and do, this is the force between sled and ground, they'll do a subscript G here, this is boy and sled, they'll do a subscript S here. That's fine, just, I tend to do it, sorry, top going down. Again,
Would,
scars.
would there be one for the dad and the ground?
I hope so. Is he falling?
No.
So Y sub D. Done.
And then lastly is tension. So there's tension between the dad and the string, so it'll be so so from the string it'll be going to the right, and then from the
That way?
yeah.
Would be holding, the man holding to
It'll be like,
towards the rope and then the rope toward, and the other one towards the man.
So at that angle?
yeah. It'll be
Are you proposing this, or are you proposing that?
the second one.
Second one, yeah. It is parallel to it's along the line of the straight rope, or whatever it happens to be. So there will be a tension acting here, and a tension acting here.
And then the opposite.
Yeah, for the sled.
Is it the rope holding the sled or the kid holding?
The sled.
Okay, yeah. That's it.
The biggest mistake I see here from students who recognize the tension is that they draw the arrows towards each other like this because of how I drew the individual object. The forces are going in that direction because the rope is really here, or the band is really here. So the forces here go like this, they do not go like that. But that's tension. I have one rope, I got something at both ends, done. Oop, wrong one. And now friction.
Friction would just be the sled and the ground, right?
There would be one over the
Yeah,
mat.
there is friction there. So which way is it acting on the sled?
On the left. So from the sled will be to the left, the ground will be to the right.
What is it?
Go that way.
Yeah.
And then,
Would it be the same for the dad as well? Because the dad is moving in there's contact and desired relative motion, so there'll be one for the dad as well, right?
going that way on the dad?
Yeah, because the dad is going to the right side, so the friction has to go to the left side.
All right, let's think about that for just a moment. Don't write this down yet. If we have friction acting this way on the man, because he's going to the right, friction's acting to the left, that seems to make sense. Except if he's accelerating to the right, there has to be a net force to the right. Newton's second law, F equals ma. Force and the total force acting on an object and the acceleration are in the same direction. If that's the friction, what force is to the right? All right, we got a problem there. Unless, did you?
Can you repeat the question?
In which direction is the friction acting on the dad? Now, Robin speculated the dad's moving to the right, therefore friction's acting to the left. That seems to fit what we were doing. However, if friction is acting this way, we don't have any force acting to the right. There has to be a force acting to the right because that's the direction of acceleration. So friction is actually acting this way. But how does that jive with the idea that it opposes the relative motion? What part of the dad is touching the ground?
His feet.
Which way is the foot wanting to move?
To the right.
Oh, it's moving backwards because
Oh, it is.
If you're walking this way,
your feet is moving backwards, but your body is moving forward.
yeah, body's moving forward because of friction. Try walking on ice. So because the foot wants to go this way,
Right.
friction is acting this way on the foot and this way on the ground.
So we're moving
Now,
because of
there is a small mistake in the way I drew this. I should have the back foot on the ground and not the front foot. I'm gonna make that change. And hopefully not screw it up too much. All right. Now,
So does that mean we're moving because of friction?
Yeah. More of
pardon?
So does that mean we're moving because of friction?
Yes.
I don't get what you mean the foot wants to move backwards.
All right,
Your feet push back,
It
yeah,
doesn't go backwards.
pardon?
but it pushes back towards the direction. Cause like, if you're pushing something, then that means
All right.
you're like.
That's why people fall in the chair.
Oh, it's cool. I've had only one table collapse, and I wasn't on it. So as I'm walking forward, I'm pushing backwards with this foot.
That's probably the worst place.
They made me do it. All right, so I'm right here, as I'm stepping forward, my foot is pushing that piece of paper backwards. That's the friction. So because I'm pushing backwards with my foot, friction is acting this way on my foot. Relative to what I am touching, my foot wants to move backwards. That is what the friction opposes.
Okay, so last class when I asked you to get on the table, you didn't, but now you're just gung ho all of a sudden?
Yeah,
So is this cause you're on ice?
If you're on, it's gonna be true for walking on carpet or whatever else. Just on ice, it's a lot more difficult to move forward because your foot is slipping backwards. Now, any questions on that before I make it more complicated?
Would it be the same for the car as well? So like, there's no sled, there's no nothing, it's just a car. Would that be the friction as well?
It would be friction as well, because the engine is trying to make, so if I'm in a car and I wanna go that way,
Uh-huh,
then the engine's gonna try to make the wheel turn like this.
yeah,
Even though the car's going that way, it's going that way because of friction, driving on ice. Because it's the tire that is touching the ground, and the tire wants to go this way,
that's why you're propelling that way.
and friction is trying to oppose that by pushing that way.
Okay. So that's why you can slide.
Okay, let me make it more complicated, despite the eye rolls I'm getting from Margaret. The tires that are controlled by the engine